So for this talk, the slides, the file you can find in the FMRI handouts directory. It's called FMRI 22. So that's the file, the PDF file. So that's the one. So this talk will pretty much focus on the individual subject analysis. So this is the layout of the talk. First, we're going to spend, I don't know, probably 20 minutes or so to talk about some basics about the regression analysis. Then we're going to switch to the basic, the model at the individual subject level, which is the typical time series regression. So for that model, usually we have this, we're writing this matrix vector format. So that's on the left-hand side, we have the data from the scanner after some pre-processing steps. On the right-hand side, we have the design matrix, multiply the effect estimates, and plus the residuals. So with the we're probably going to focus a lot, spend a lot of time on the design matrix, because we call it design matrix. That's because usually there's a lot of observational data. It's something you design the experiment. You want to get something out of the data, so you design the experiment. That's why the terminology of design matrix. Within that design matrix, you have multiple columns. Some of the columns are specifically about your experiment, right? So that's your tasks or conditions. Some of the columns are of low interest. You don't care about them, but you do want to put in the model to explain some of the effects from those regressors. So that's the design matrix. Then the betas are pretty straightforward. That's we care about. That shows how much you expect to see in the brain. Lastly is the residual part. Residual part we don't care about, but we do need to be a little bit careful about it. We also spend a little time to talk about the residuals, because the conventional regression model, the residuals, we assume they're white noise. White noise, that means there's low data structure, low temporal correlation, for example. But in FMRI, that's not the assumption. Usually does not hold well, so we need to do something special about that part. So the next thing about the design matrix, for the stuff we don't care about, then we still have break into three subcomponents. One is the baseline, one is the slow drift, some people call it low frequency components. Then other stuff usually it's like head motion parameters, right? So we usually try as much as possible to correct for head motion, but that step usually is not perfect. So we still need to consider incorporating some of those head motion parameters into the model. In addition to that, there's something like in FMRI specific that's you may want to censor some time points if you consider those time points a little bit too much. For example, head motion or scanner irregularities. So that's called the censoring part. That's probably something FMRI specific. So that's those are the different types of regressors of low interest. So then we talk about the regressors we care about. Even for that, there are different concepts. That how do you want to model those tasks or conditions? That's a little bit tricky. So that's the effective estimates. So there are three categories. One, the big one, and the popular one, and probably 99% of the time, people just make some assumption, assume that's your hemodynamic response. Just use whatever available in the software, then assume that's the response curve. It's the same everywhere in the brain. It's the same for everybody, for all the subjects, regardless of the tasks, regardless how many trials you have. You always assume that is under the curve. So that's a big assumption. That's called a fixed shape. Then there's some little bit more flexible. That's usually SPM adopts that approach. You have one, they call it a canonical curve, then plus two additional one. Sometimes people use one extra, which is the time derivative. Sometimes they use the third one, which is the dispersion curve. So we're going to talk about that modeling approach. Lastly, we're going to talk about the most flexible approach, with which you don't make any assumption about the response curve. Don't make any assumption about the shape. You use the data to model the shape. So that It's the most flexible, but it's the most challenging one. People don't use it because they are, in the end, people don't know how to do group analysis. So that's the tricky part. So we'll talk about that. Then if we still have some extra time, we're going to talk about some miscellaneous aspects of like multicollinearity. Then we have practical issues like you have multiple runs. How do we handle it? That's also something FMRI handles a little bit slightly different from the other software packages. Then lastly, there's a concept of a percentage signal change. That's how you normalize your data or scale your data. That's also a little bit unique for FMRI because in the end, there's a how do you interpret the beta values? That's not just the interpretation, I mean from conceptual perspective and also from modeling perspective, you do want your betas compatible across different subjects, across the brain regions. Otherwise, if the betas are not interpretable, why do you need to do group analysis, right? So that's something we will talk about. So that's basically the big picture of this talk. So now let's start some basics. I mean, everybody here, pretty much everybody knows FMRI data, and you already learned some statistic basics, right? Regression model, there are different terms. Some people call it linear model, some people call it general linear model. There are some subtle differences across those terms, but let's just ignore. Let's just assume everybody talk about the same thing. Traditionally, regression model is the simplest one. You have Y, which is the data we call it, traditional people call it dependent variable. The X is called independent variable. I think nowadays those terms are fading away because when people say that there's some causal relationship implied in those terms, so that's not necessarily the case. So usually we tend to say the Y we consider it as an outcome variable or a response variable. X, we usually say that's your explanatory variable. So the simplest regression model or linear model is just we have one explanatory variable. We look at how much the X can explain the variability in the Y. So that's the simplest model. So on the right hand side, it shows such a simple curve, right? So we have some pairs of X and Y. We try to fit it with a straight line. That's why it's called a linear model, right? That's pretty straightforward, but let's just repeat that intercept. Each straight line we need two parameters. One is the intercept, the other one is the slope. The intercept, we're going to come back to that, especially at the group level. At the individual sublevel, that intercept usually is the baseline, right? We don't care about, but we do need to put it in the model. The slope, that's in general, the linear model slope shows the marginal effect. When the X increases by 1 unit, what's the amount of change in Y? But for FMRI, we deal with the model. It's a different framework in the sense that the X and Y is not just the simple pairs. Also the X, especially the X, there's some pattern about the X. The X is our regressors. It's something we put in the data. That's your design experiment. You at which moment, like for example, at 10 seconds, you ask the subject to do something, right? So there's some pattern. That pattern is usually we call it as several regressors. So that's why when we write in this vector and matrix format, that probably a better way to describe the FMRI data framework. So the simplest case, of course, is just an intercept plus one explanatory variable. So that's still the simplest case. In FMRI, we deal with way more complicated than that. So we'll come back to that later. How to look at how to formulate the design matrix. But once we have that model, we solve it. So the simplest case, traditional approach, we solve the numerical term solution is called ordinary least squares, right? Basically, you try to search the possible betas. Like fit the data makes the residuals as small as possible. right? So that's why it's called ordinary least squares. Squares, that means the residuals are not just add up. We need to square them. Why do we need to square them? Because some of them are positive, some of them are negative. So that's why we need the squares. So that's why it's called ordinary least square. Least, that means their optimization, which is minimize the sum of the squares. So once we solve it, then we estimate the beta values. So it's geometrically speaking, it's pretty much like people call it a projection. So we have the data. The data is this arrows, right? So that's your observed y. What we can explain is our design matrix. So the data is at a higher dimension, but in this case, it's 3 dimensions. So what we can explain is that this blue plane is a 2-dimension. So we projected a 3-dimensional object onto this 2-dimensional plane. So that's your faded part is this faded y. So the difference between the two is this. That's the residual part, right? So what this part is y times this vector of 1s. That's basically the baseline. The intercept part. So that's just a different perspective. So once we solve it, then for FMRI, usually we not just solve estimate the betas. We also want to see how confident, how much evidence we can see in this particular brain region is that we can say with some confidence, say this region is activated or not, right? So that's one possibility. Or we can compare 2 conditions, like you have house image versus face image. In one particular region, maybe it's house dominant region, then we want to check the difference between the 2. So that's usually we do a contrast. Occasionally, you may do more sophisticated case. You can linear combinations of multiple beta values, right? So those are typically we call the t-tests. Those scenarios. Occasionally, we may do something even more peculiar. Peculiar is like this. Whether any of them are equal, all equal, those 3, or equal to 0. So those are usually we call them a composite null hypothesis. So we would have to resort to f-tests, Fisher's f-tests to test the significance. The regression model, there's also the concept of omnibus test that shows a bundle of regressors, or all the regressors, depends on the context. So that's basically the scenarios you may encounter when you perform statistical testing. This is basically the traditional approach. People call it null hypothesis significance testing, NHST. So you make a straw man to attack that straw man. That nobody cares about the null hypothesis, right? So for beta is 0, nobody cares about. But the traditional statistics is that we put up that straw man to attack it, pretend that nothing going on. So that then we find some, based on the data, we see that's that null hypothesis is not reasonable based on our data. So that evidence is usually the statistic like T or F. So the T is high, then we say, this is not reasonable, so we can reject that null hypothesis. So then we take the alternative, which is called the alternative hypothesis. So now that's why the concept of a p-value, right? So the p is associated with the so-called significance. If you say the significance is 0.05, then that's why the magic number, 0.05. Why is the 0.05 so we need to worship it? Why? Just because probably in 1920 or 30s, Fisher decided, it's basically at that point he said 1 out of 20, right? So that's why that's the magic number. Nowadays, we have to suffer that. Everybody has to pass that threshold. We'll come back to that subtlety later on, during the group analysis approach. So that's the big picture. You have the model, you solve it, then you perform some statistical testing. So for FMRI, the Y is a little bit different. It's not just some random, some observation of data points. They call it time series. That means there's some spatial order, right? So they're sequential. So that's a time series. That's why sometimes we call it time series regression to emphasize that there's sequential or serial order among those data points. Not just the data we collect from the scanner, also this has impact on the residuals because the residuals may also have some temporal structure. That's why the traditional approach of ordinary least squares is not good enough. So that's basically that's why this issue we have to be a little bit careful. So we solve it, but remember we not just solve one model. We have many models, as many as the number of voxels in the brain. So suppose we have 200,000 voxels in the brain, we'll have to do it 200,000 times to solve the same model. By the same model, I mean on the right-hand side, the design matrix is the same. But on the left-hand side, the Y is different at each, cross voxels. So of course, in the end, the betas are different. So that's some background. So I guess everybody's familiar with the FMRI experiment design, right? So whenever you design experiment, you need to recruit some number of subjects. That's a sample size at the group level. At the individual level, you design experiment. You know how many tasks you put in the model, right? So like house phase, you have two conditions or two tasks. Each task you're going to repeat some number of times. That's called the number of trials, right? So that's the sample size per condition or per task. That's at the individual level. Then each task, each trial, that's the concept of whether it's a block design or event-related design. The differentiation is those two it's just arbitrary. People say event-related design simply because the duration of that each trial is about 1 TR or less. If you're longer than that, that's people usually call it a block design. That's just for convenience of when people describe a design. Sometimes you have mixture, right? So you have a queue, right, to show the subject to tell them something is upcoming, right? So the queue maybe just 500 milliseconds or even shorter. But then later on, the real task may last a few seconds or even longer. So you could have a mixture of events and blocks. So there are a bunch of other terminology I'm going to skip. But lastly, I want to say there are concept of runs and sessions. Run, across different runs, that means usually you scan the subjects, but usually they cannot stay in the scanner for, like, for example, 1 hour. Right? That's just too much. So you need sometimes just stop the scanner, but the subject remains in the scanner, right? Just stop the scanner, take a break, a few minutes break, then start again. That's called multiple runs. Sessions, that's usually you stop the scanner, the subject also gets out, then come back later or next day or even a few days or a few months. So that's called different sessions. Block design, the difference between, I already talked about that. Then, so once we have the model, we have the data from the scanner after we pre-processing. Then basically we break into multiple components, right? So we have the signal part and the noise part. So the signal part, I already mentioned that you have the baseline, you have the slow drift, then you have a few regressors, which usually the head motion parameters or sensor the time points, then plus some multiple conditions or tasks. That depends on how we model it. So that's basically the structure of the model. So this is one specific voxel which I believe Daniel or Rick showed you earlier this morning, that this is some voxel in the brain here. It shows the black curve is the original data, right? The red one is something we expect to see in the data. The blue one is we use the red curve to try to match the black one. So the blue one is our best fit. So, this shows how noisy the FMRI data is, right? So it's really a little bit hard. This is a block design, is a little bit better than event-related design, but still it's difficult to say the pattern. Also, you notice that there's some drift, right? Not just the block design regular pattern. There are also downward drift. That's the part we also need to take care of it. So in this case, 20 seconds on, 20 seconds off. I mean, even this, we make quite a number of assumptions. First of all, during each block, the both signal really stays like this, a plateau. But that's our assumption. In reality, whether that's true or not, probably I doubt it. I mean, we know you cannot, even when you sit in the classroom, you cannot hold your attention all the time like a flight line, right? So we know there's a habituation effect. You get fatigue, right? So, but anyway, that's first assumption. We assume that plateau. That's a level. That's probably not the practically reasonable assumption. But anyway, we do it. So that's one. Also, we assume cross trials they are exactly the same. That's another assumption. So those are the two big assumptions. But anyway, that's the simplest model we can try it. So that's a block design. This is the event-related design. I mean, the upper one is presumably it's a voxel which is responding to some tasks, right? So there's event-related design. This the red curve again. The black one is the orange data. Red one is something we expect to see. The blue one is the best fit, best match as much as we could. So this is the voxel presumably is activated versus the one down below. It's another voxel which is not activated. Simply compare the two black curves. I mean, it's really difficult to say which one is activated or not. That's because, I mean, first of all, it's when event-related design, those trials, each trial lasts a really short period of time. So it's really difficult to say the pattern. Plus, the pattern itself is pretty, because when we usually design experiment, we don't do it like this way, a regular on and off. This is not a good design. Usually we want to randomize those trials for two reasons at least. One reason is we want to avoid a confounding effect with the slow drift. Because there's slow drift there, we want to avoid that, the regular pattern. That's one reason. Another reason, we want to avoid anticipation from the subject. If the subject knows every 10 seconds I'm going to do something, that anticipation is, we want to avoid that, right? So that's one, I mean, both of the two major reasons when we especially design event-related design, we have that pretty random pattern of the so-called the idealized response. I mean, in addition to this, I want to say the signal, the real signal embedded in the EPI data is pretty much low. For block design, maybe you could reach up to 50%, but for event-related design, probably we can only explain about 30% of the data. The rest is, we call it noise, simply because embarrassingly, I mean, we don't know much about it. We just bundle them, we call it noise. Well, that comes to the concept of, how do we create a regressor, right, for corresponding to a specific task? That's called the concept of Bolt signal. The Bolt signal is not the neuronal response. It's something, some indirect measure of the neuronal event. So that Bolt response is basically that's why it's a sluggish response curve. That's because it's not direct measurement. So it's the oxygen, blood oxygen content in the blood. I mean, so that's why it's much slower, sluggisher. So there's that curve. But what's so special about that curve? Well, let's start with the simplest case. It's just the so-called event-related design, or in spontaneous event, just lasts pretty short period of time. How short doesn't matter. So it's like here we have this red arrow on the left-hand side, left corner. Suppose we show something on the screen for a short period of time. So we expect the bold response, the signal is this sluggish curve, right? So in FMRI, we call it gamma variant, that curve. That curve, the mathematical formula is like this. But is that some magic expression? So there's this t to the power of p and multiply the exponential part. There's two parameters, p and q. Is this something like in the physics, we have some gravitational constant? No, there's not something like that. The p and the q, there's low, even though there are some specific values like here, p, this particular case, this is 8.6, q is minus 0.547. Those numbers, 8.6, they don't mean much to us. They don't describe some intrinsic properties about the blood flow. No, not at all. They're just an empirical curve. Just try to, roughly, we can do some reasonable job with this fitting. So here we have this t is the time, plus the exponential. They don't mean much. We don't really expect to show there's something related to neuronal response. No, not at all. So it's just an empirical curve. So we use this curve as a mathematical convenience. So with this curve, we can convolve with the stimulus timing. That's a mathematical concept of convolution. It's pretty much like multiplication. So that's why this sign is a multiplication sign with a circle surrounding that sign. So that's, in FMRI we have multiple, we call it basis functions. It's to describe try to characterize the hemodynamic response. One is called gamma variant. We also have implemented the SPM one that's called a canonical curve. Right? So the main difference is there's a called undershoot during the recovery part. That's one thing. Another thing is I think the duration lasts much longer because of the undershoot. So the main part is roughly about the same as 14 seconds. But after 14 seconds, the canonical curve in SPM, there's this undershoot, so it extends to roughly 25 seconds, the whole duration, because of the undershoot. So you can choose whatever you want. Both options are available in FMRI. That's the basic. Suppose you have an instantaneous event. How about you have a trial lasts a few seconds? That you can conceptualize as multiple events. At each TR you have an event. Then basically you convolve them or you add them up. That's why those 5 colored curves. You add them up, you end up with this black curve. So it's basically the summation of those five copies. So this is you have 10 seconds the duration. So this there's a subtle difference between you use even for short event in FMRI you can use GAN. That's basically regardless the duration. Usually it's one TR or less. But for Brock, but you could use Brock. There's an option called Brock. Use the Brock to specify the duration. So even it's a short duration, like 1 second, you can still use this Brock option with a parenthesis with the duration specified. So that's even though it's a Brock. The concept of Brock is pretty arbitrary. It's so that's I think probably later on Rick can show you how to specify different basis functions. All right, so here is a simple case. You have Brock design 20 seconds on, 10 seconds off. So you end up with this regular pattern of multiple trials. So that's a Brock design. So you use this option Brock, 20 seconds, that's the duration. The second parameter 1, that's definitely we usually in the end, regardless the duration, you scale the regressor with the maximum magnitude of 1. So the reason we do that is the beta would be a multiplier. That would be you can interpret the beta as a percent signal change. Basically, we use each regressor as a ruler. So it's a unit, a standard unit, right? So that's why we always, pretty much always scale all the regressors with a maximum magnitude of 1. So that's the reason. So that's a block design. Then this you have event-related design, but you have multiple events that separate with randomized, right? So here we have 4 different events. So that's a same task, but you repeat 4 times. So when you create a regressor, you don't create 4 regressor. Maybe occasionally you do, but usually we create 1 regressor for all the 4 events, right? We don't care about each individual trials. We care about the average or the general pattern of the whole task. So that's why we convolve them. That means we add up all the individual 4 trials. We end up with this black curve. So that's basically the summation of those four individual copies. So that's a event-related design. So in the end, we have this in the model. We take care of those regressors of interest, right? Now let's go back to talk about the baseline slow drift plus the other regressor of low interest. Baseline is nothing magic. That's just something that we always put the intercept in the model because the baseline is something we start with, right? So slow drift. There are a few possibilities. Why do we have slow drift? One possibility is the subject itself. Subject may have a physiological effect. The 2 major ones is breathing. The other one is heartbeat. Breathing, both breathing and the heartbeat, because especially probably the first time when we get in the scanner, maybe a little bit nervous. The heartbeat is faster, breathing and also faster, right? So, but after a while, you calm down, right? So then that's why that is slow drift. So it's not the fluctuation, but the long range effect. So that part. Then there's sometimes they have slow moving. It's not the jerky movements, but the slow drifting head motion. Plus the scanner itself may have thermal drift effects. So that's the slow drift. In FMRI, we do it probably slightly different from the other software packages that we model the slow drifts with polynomials. I believe the other software packages use high-pass filtering. So high-pass filtering, you basically use theoretically speaking, in the end, you put it back, filtered frequencies back into the model based on the frequencies. So I believe the default for them is 128 seconds. That's the cutoff range for the slow drift. I would not think that's a lot have any substantial differences between the 2 approaches. But anyway, in FMRI, we have the baseline. Basically, the baseline is part of the polynomials, right? So you have the 0 order polynomial, the intercept plus the linear drift, or depends on how long each run, the duration of each run. You could use just linear drift, or use quadratic, or occasionally use cubic. That depends on the duration. So the general rule is that if you every 150 seconds, you add extra order for the polynomials. So that's a slow drift. Then the head motion, that's pretty much standard nowadays. Also, when you have multiple runs, of course, each run has its unique drift effect. So that's why each run, you would have if you have quadratic, so then each run you will have 3 parameters for the slow drift. If we have 2 runs, we would end up with 6 parameters, right? Six terms for 6 regressors for baseline and the slow drift. So that's head motion. That's this is the impact of example of a head motion effect. On the left hand side, if you don't take care of the head motion, versus the right hand side, we put it either, for example, 6 regressors in the model. That's sometimes you show that difference, clean up the situation a little bit. So the next 2 slides, we show different ways to check your design matrix. So remember, we have this model y equals x, that design matrix, times the beta values, the effective estimates plus the residuals. So the x is the same for the whole brain. For every voxel, we share the same x, but y is different, right? Each voxel has their own time series, the response variable. Beta, of course, is different cross subject. Residual is also different. So suppose we have this modeled x, we have the baseline, we have leader drift, plus a bunch of other regressors, right? So this would be an image of the design matrix. So I think this probably everybody familiar with this because the other software packages adopt the same way to visualize the design matrix. So in FMRI, probably the pattern, I mean, you're familiar with this, you know the pattern, right? So in this case, we have 3 rungs. Each rung, we have 2 regressors. One is the intercept, I mean the baseline, one is the linear drift. So that's why the first 6 columns are for the slow drift. So that's why, and also you can see this 3 segments, right? So the big pattern. The baseline, of course, is uniformly black. This is the linear drift, so you go from white to dark gradually. So it's the linear drift. For the rest, that's the first rung. So that's why second and third rung you don't have anything. Same thing, we switch to the second rung and third rung. So that's how the baseline and the slow drift look like. So the next 2 columns, we have 2 tasks in this case. So we see some regular bands, not regular bands, but some bands. That's block design pretty much. So the last 6 columns are the head motion parameters. So 3 translations plus 3 rotations. So any questions? Yes?
I don't understand why the head motion is laid out in these random bands. That's just because you're going to get that from your image where the motion came from?
Yeah, came from. Yeah, that's how they are, okay. How they look like, yes.
Okay.
I mean, personally, I prefer this way instead of image, but they may have different perspective. I mean, it's a personal preference, but this, to me, I like this more because, it shows the pattern even better. So the way, definitely there's, once you run, after you perform the, we call it volume restriction, registration, the other software package, they call it head motion correction. But anyway, same thing. Once you go through that step, you end up with 6 regressors, right? 6 parameters. So you can, actually, this is not just that. In FMRI, when you specify your model, the program will generate the design matrix. You can use a program, it's called a 1D plot. Because it's not 3D because we're dealing with one-dimensional data. So that's why it's called a 1D plot. You can use that program to plot this out. Actually, in Rick's program is FMRI plot.py. I think that automatically generates when you examine your data, you automatically plots out the panel like this. So the way you look at it is it goes from the bottom to the top. From the bottom, you start with all your baselines plus the linear drift. The drift. In this case, the linear drift. So the baseline, the bottom one is this black one, is the horizontal line. That's first rung plus the linear drift, right? So that's the first rung. Then you switch to the second rung, then the third rung, right? So the bottom 6 curves are the baseline plus the drift for the 3 rungs.
And you pull out that baseline again from your data, you do like a low pass filter and you see what that drift is, or you do a linear fit to the whole?
We'll do linear fit for each rung. Yeah, in this case, I don't remember, probably 200 seconds, I don't remember, but yeah. That's just empirical data. It's ideally, not just we'll talk about the slow drift, even the tasks or head motion parameters. As a statistician, I would do, the process, not just, very unfortunately in FMRI, people we have a model, we run, then we just talk about the result. As a statistician, usually it's not just a one-time deal. You need to go through multiple steps, multiple rounds of model building, model checking. I mean, but unfortunately, I mean, it's more like a assembly line for typical users. But we can come back to this issue later on at the group level, talk about how to do model checking. But so ideally, even for the slow drift, you could check those betas, whether you see something in the brain, and run another model with a higher order polynomials, compare the two models. I mean, you could do something like that, ideally, yes.
So Apple has this 3D trend pre-process, right?
Right.
So would you recommend we model this for the drift, or recommend us use the trend, or both?
No, I don't recommend to do it as a pre-processing step. The reason is that usually we want to put everything in one model. That's the ideal situation. So the pre-processing, that's because we don't have a better way to do it. We do need to clean the data to some extent. So, but we want to avoid that as much as possible, right? So like, for example, during pre-processing, we do slice timing correction. That's basically we artificially align those multiple slices, right? When we acquire the data from scanner, each slice is acquired separately. We don't take a snapshot of the whole brain. That's not the way the scanner works. So one slice, second slice. I mean, there are different orders, but anyway. So we need to manually to align them, put it at the beginning of the TR. So that is just for easily for us to build up the model, right? So that's a pre-processing step. I mean, smoothing, same thing. But for the train slow drift, we don't want to remove the trend first, because those trends may correlate with some of the long-range drift from the regressors of interest. They may correlate to some extent. That's one reason. Another reason, I mean, you can talk about degrees of freedom issue. I mean, so ideally, you don't want to do that. Sometimes we do have to do it like for Wilson's data, because Wilson's data we don't have a better option. Any other questions before I move on? So the next two rows, the red one and the black one, those are the regressors of interest, right? So immediately we see the pattern here. So this is the better way probably to visualize, to check whether you make a mistakes or not. I mean, mistakes by you put a wrong stimulus onset time, that will mess up your model, of course. So the last six rows on the top are the head motion parameters. You were asking before whether here you can a better way to see the pattern, right? So whether you have like big dip or big jump, that's in this case, of course, it's because of the different runs between different runs, right? Also, I want to say here in FMRI, it's a little bit different from the other software packages. When we have multiple runs, usually we glue them together, and for example, we only have two regressors here, even though we have 3 runs. So that's something unique about the FMRI. I will come back to this point later on. So that's something we need to pay attention to. But so the other software packages, either you have to analyze each run separately. I believe that's the situation with FSL. In SPM, you can concatenate them, you can glue them together, but you have to model each run in a model. Like you would have 6 regressors of interest instead of 2. So that's the difference between FMRI and SPM. Any questions about this? All right. So I mean, there's a little bit of quality check. I mean, when you run FMRI, I mean, Rick will talk about this in more details. You're going to see on the terminal on the GUI or whatever, you are going to say something about the progression of the model solving process. Like you see some warning is something you need to concern, or if there are error message, so that's something you need to pay attention to, right? So model building, I mean model checking, there are many ways to do it, but probably Rick will talk about some of it later on when you specify the different options and check the model quality. So far, I have only talked about one modeling approach, is that we assume the response curve is some, whatever you call it, standard curve or canonical curve. That shape is fixed. So the curve goes up slowly, reach the peak, then recovers even much slower than the upstroke. So that curve, I mean, I said something, I mean, critical about that approach, because, I mean, we believe that, I mean, we assume that curve fits reasonably well. It's the same for different subjects, or even males or females, patients or controls. It's the same curve shape, right? Different brain regions, it's the same curve. Different tasks, it's the same curve. Different trials, it's the same curve. So that assumption is very strong. Is there any way we can relax it? Yes, there is. So that's the approach we're going to talk about later on. I think let's take a break, 10 minutes break, then we come back to talk about the alternative approach, how to handle the hemodynamic response with a little bit more flexible, and I mean, not just for better model, and also capture some subtleties about the hemodynamic response. All right.